Uh, so last lecture, we have proved a very important proposition. Let G, H be a Riemannian symmetric square with Cartan decomposition G is equal to K plus P, and let pi from G to G mod H be the projection map given by pi Z is equal to G H, and O is equal to pi E is equal to H. Then d pi E from P to T naught G mod H is a linear isomorphism, and d pi E commutes between two H actions. That is dl H naught composition d pi E is equal to at GH composition d pi on P for H belongs to H. Moreover, there is a one-to-one correspondence between the following three sets: H invariant Riemannian structures on G mod H, and H invariant inner products on T naught G mod H. That is a one-to-one correspondence with the set of all odd GH invariant inner products on P. Moreover, there is always exists a G invariant Riemannian metric Q on G by S. And we have also proved an important theorem that let G, H be a Riemannian symmetric pair associated with involution sigma G to G. Let pi from G to G mod H be the canonical projection given by pi Z is equal to GH. Let O is equal to H is equal to pi E. Then in any G invariant Riemannian structure Q on G mod H, which always exists, G mod H becomes a Riemannian symmetric space, so that S naught composition pi is equal to pi composition sigma, and L of sigma G is equal to S naught composition LG composition S naught. Okay. And I have remarked in the last that this geodesic inversion doesn't depend upon the choice of G invariant metric Q. Okay. So this is interesting, of course, but at the same time, it may confuse you because the geodesics are dependent. It seems that geodesics are dependent upon the Riemannian metric, and so it is really. So you must look. You must be wondering that how the geodesic inversion doesn't depend upon Riemannian metric. So I have for that reason actually I have given an exercise. Let M be a smooth manifold with two Riemannian structures Q1 and Q2, and Q1 is not a scalar multiple of Q2. Is it possible both MQ1 and MQ2 are Riemannian symmetric spaces? And supposing your answer is true, is it possible that geodesic inversion are same? I have also added one line later that think about it without using the above theorem. If you will use this above theorem, it is sort of trivial in the sense that the thing is G invariant Riemannian matrix are one-one correspondence with H invariant inner products on T naught G mod S, and H invariant inner products on T naught G mod S is one-to-one corresponds with RGH invariant inner product on P. If the isotropy representation is not reducible, so it may possible that you can choose two inner products on P which are RGH invariant, and one is not scalar multiple of other. Okay, and then you use those two inner products to produce G invariant Riemannian matrix, and those matrices will not be scalar multiple of each other. And with those two matrices, the abstract theories, that theorem says that that becomes a symmetric space. G mod H becomes a symmetric space, and those Riemannian matrices are not really scalar multiple of each other, and the geodesic inversions are same. So what I'm saying on P,
you symmetric space in the last exercise.
Last lecture is not symmetric space. This is some smooth manifold.
Okay, but if it is symmetric space, then it is unique. Huh?
No, that is the question I am addressing it. Okay, so I will tell you.
No, you would get a k add k k invariant inner product.
What I'm saying that listen to me.
If your M is symmetric space, then K is your compact.
Then what? Yes.
It's not it true?
It may happen that there may be K invariant different inner products are there. Maybe more than K invariant inner products there.
But is it not irreducible? Will not be that irreducible.
That's what I am saying. That if P, the RGH action on P, this is not irreducible. Suppose.
But your H is here compact, is it?
in the symmetric space case, it
Yeah.
is compact, but in Riemannian symmetric pair, it is not compact.
Okay.
If it is compact, even that will not solve the problem. Okay. So this is suppose RGH action on P. Suppose H is compact for a moment assume. This is not irreducible. You can choose two different inner products here. One say 1, 2, so that this is not scalar multiple of this. Okay. Now you can use this inner product to get a G invariant Riemannian metric Q1, and you can use this inner product to get a G invariant Riemannian metric Q2. Okay. If you look at the statement of that theorem, that it says that in any G invariant Riemannian metric Q, this is a Riemannian symmetric space. Okay. So in Q, if you look at this thing, G mod H Q1, this is a Riemannian symmetric space, and G mod H Q2, this is also a Riemannian symmetric space. Okay. So the question is, by this theorem, it is saying that abstractly this is possible. Okay. But I just wanted to do this exercise without using that theorem, and some examples, and you just take some examples and tinker with those things so that your understanding will be better. I will do this exercise later, but I just want all of you to think about it. Okay, so now the thing is, let us come back. So let M be a RSS. Okay, let MQ be a RSS, right? Riemannian symmetric space. And let G P belongs to M. G is really I am not, and K is equal to really stabilizer of P inside G. Then sigma from G to G is okay. Let sigma from G to G be given by this sigma G, real SP GSP. Then this GK is a Riemannian symmetric pair. We have seen that. Okay. Then by the previous theorem.
You mean RSP?
Oh yeah, RSP. Sorry. RSP. Then by this previous theorem, okay, in any G invariant matrix Q prime, this M prime is really this G mod K is a Riemannian symmetric. So now we can identify M with M prime as a smooth manifold, right? Smooth manifold we can always identify there is nothing. Now so MQ is a symmetric space, MQ prime is also symmetric space. Now question is whether is it true that MQ is isometric to MQ prime as a Riemannian manifold. Both are symmetric spaces. Okay, so Riemannian manifolds, and it is also clear that if the Riemannian matrix agree at the base, if it is also clear that if QP is equal to QP prime on TPM, then Q is equal to Q prime. This is clear because of the G invariance. Now the thing is, I want all of you to think about this question. I will answer maybe in the after 1 or 2 lecture. Okay, so this is a very interesting question. Okay, so now we come back to our thing which we are discussing. So we started with a Riemannian symmetric space. Then we get a Riemannian symmetric pair. Okay. Now conversely, we have got this thing. Riemannian symmetric pair. We get a RSS, Riemannian symmetric space. Now, if you look at the definition of the Riemannian symmetric pair, where actually we do not really demand this H to be compact. H is not necessarily compact, and we will produce some examples here. Okay, so where H is non-compact, but if some Riemannian symmetric pair we are constructing out of a Riemannian symmetric space, then H is necessarily compact. Okay, so that means this set, this collection of RSP, okay, is a sort of bigger. If you look at the collection for RSS and collection for RSP, this collection is really bigger. And this, there is a correspondence, but this correspondence is not really not one-to-one correspondence. Okay. So if you look at in this direction, this is really, this will be 1-1 and not on 2 in this direction. And in this direction, this will be on 2 but not 1-1. We will produce many examples, but this thing you have to really keep in mind. Okay, so this is a set of all RSP is a much bigger collection. 2-3, it may happen that more than one Riemannian symmetric pair may give rise to one Riemannian symmetric space. Okay, we will see some examples. So before that, so this is the okay. So now we want to produce some example. Before that, we really little bit recall something about classical Lie groups. So let G subset of GL and C be a matrix Lie group. That means G is a closed subgroup of GL and C. Therefore, G intersection UN is closed in UN. Now, as UN is compact, and therefore G union intersection UN is compact. Okay. Now I want to prove a proposition. So let G subset of GL and C be a matrix Lie group, so that G admits a polar decomposition. Bipolar decomposition, I mean something like this. That is G is equal to homeomorphic to G intersection UN cross G intersection P and C. Okay. Sorry, this is really homeomorphism. And where P and C what? Where P and C is the set of all complex positive definite matrices. Definite matrices. Then the proposition will say that then G intersection UN is the maximal compared subgroup of G. Is a maximal compared subgroup, is not. Okay, so proof is very simple. Proof Suppose let K tilde be a compact subgroup of G, so that K tilde properly contains G intersection N. Properly contains this thing G intersection UN. Okay, so now so this implies there exists some G belongs to K tilde with G doesn't belongs to G intersection UN. Now bipolar decomposition. I can write G is equal to some UP where this U belongs to G intersection UN and P belongs to really, oh god, and P belongs to G intersection PNC, right? Now this thing U belongs to really G belongs to K tilde and this U belongs to G intersection UN and G intersection UN is subset of Q tilde, K tilde, so therefore P belongs to Q tilde. Since G belongs to K tilde and U belongs to G intersection UN, this is subset of K tilde, and since K tilde is a group, so this P belongs to K tilde. Now as G dot dot belongs to G intersection UN, so this and U belongs to G intersection UN, this implies P belongs to G intersection UN, right? P does not belong to G intersection. So this implies P is not equal to identity. Okay. Now as P is a positive definite matrix, so P can be unitarily diagonal as well. Okay. So as P belongs to PNC, so there exists U belongs to UN, so that P is equal to really U something like lambda 1, lambda 2, lambda n 0, 0, this U inverse, and this belongs to P belongs to K tilde. Okay, this is the thing, and lambda I should be greater than equal to 0 because this is a positive definite matrices. Now as P not equal to identity is not, there exists some lambda I naught, so lambda I naught is not equal to 1 for some I naught, for some 1 less than equal to I naught less than equal to n. Now I will take this P to the power m. So P to the power m will be really U lambda 1 to the power m. Okay, so let us write this diagonal of this. U into diagonal of lambda 1 to the power m, lambda 2 to the power m, lambda n to the power m. Okay, U inverse. This belongs to K tilde because P is a group, and this for M belongs to Z. This will happen. Okay. Now let S is the beset thing, diagonal of this thing, lambda 1 to the power m, lambda 2 to the power m, lambda n to the power m, so that M belongs to Z. Okay. So since this is a group, I am taking M belongs to Z. Okay. So this set is unbounded. Why? Because lambda I naught is equal to 1, not equal to 1, is unbounded. Since this lambda I naught is not equal to really 1. Okay. Now, okay, so now what is this thing? Now S is equal to really, this is really U inverse. Okay, so this is really U inverse P to the power m U, so that M belongs to Z. If you look at this thing, yeah, this is Okay. Now this is since p to the power m is an element of k tilde. This is really, this will imply that, and this is really u to the power. This is subset of u to the power u in, sorry, this is subset of u inverse k tilde u. Hello.
Yes,
Yes,
Muna.
please.
Yeah.
Hello.
Yeah, Mother, you are audible now.
Okay. Are you able to see my screen?
Yes, Mother.
So where was I?
Just if you are defined as, and now hence start. Hence, what you are going to start?
Okay. Okay. S is equal to, I have defined like this: diagonal of lambda 1 to the power n, lambda 2 to the power 2 to the n, lambda n to the power n, m belongs to Z. And since lambda I naught is not equal to 1, this S is really unbounded. Okay, because I am taking m belongs to Z. Now S is equal to, if you look at this thing, this is really u inverse p to the power m u, so that m belongs to Z, and that is subset of u inverse k tilde u. So hence S is subset of u inverse k tilde u. Then S is unbounded since u is a fixed matrix. This u inverse k tilde u is bounded, and which is a contradiction. So which is a contradiction. Thus the G intersection UN is maximal compact. Is a maximal compact subgroup. Maximal compact. So this we have proved that. Now we have really given many examples of G for which we have a polar decomposition. So and we have explicitly calculated this G intersection UN. So what I have done, I have really written down those examples. You can see that. For instance, for GLNR, the maximal compact subgroup is ON, GL plus NR is ON. Similarly, SP2NR, this maximal compact subgroup is ON, GL and CUN. So we have explicitly calculated those things, and I have really written everything here. So, okay, so let us. These two pages I have to delete. Okay, so this is the thing. Now remark, let G be any matrix Lie group which has been listed in the previous page. It is known that this maximal compact subgroup of G is unique up to conjugate. That is, any two maximal compact subgroup of G are conjugate in G. Okay, so this is the well-known fact. And we have this, I want to give also this exercise. Let Gp comma Q is equal to either OP comma Q or SOP comma Q or SO not P comma Q or UP comma Q or something like SUP comma Q or SPP comma Q. So that Gp comma Q is isomorphic to G prime Q prime if and only if this P is equal to P prime, Q is equal to Q prime, Q is equal to Q prime, or P is equal to Q prime, or Q is equal to P prime. So thus you have to really change P and Q. Then if you change P and Q, then they are only isomorphic. Okay. So using this above exercise, so we can write This HN, actually we know that this is really isomorphic to SO naught. Okay. HN is really isomorphic to SO naught n comma 1 mod SON, and you can really write this as in same thing as SO naught 1 n mod SON. So this is a important exercise. So that is the thing. Now actually we want to really prove some examples of Riemannian. We want to give an example of Riemannian symmetric space and Riemannian symmetric pair. Okay, so I just wanted to I just wanted to give another proposition which I have forgotten. So proposition.
Mona, I just wanted to ask one thing.
Yes, sir.
I don't know whether I have missed those lectures. When you talked about hyperbolic spaces,
Yes, sir.
did you talk about those three models and such things, or you just looked at this G mod K picture?
Now three models I have discussed. Actually, in the of course in the H2 case, 2-dimensional case, I have discussed three models. But the thing for HN actually I have discussed precisely this hyperboloid model.
Okay. One model.
Or for this thing actually I gave three model picture, but I told that in that thing that from a hyperboloid model to go to this model, then that is easy because that is just stereographic position.
No, I am asking for HN in strictly bigger than 2. Did you discuss three models or three models in H2 case only?
Only H2 case actually I have discussed, but in the
Okay.
higher dimensional case, you will not see any difficulty to give an means correspondence between this hyperbolic model to this model. That you can do for because that is essentially the same idea, but the difference is from going to this so-called hyperbolic and those things are very. I didn't really. I do not know those things.
Okay.
Though there are some complications. Only for that reason, actually, I have only stayed in the two-dimensional case. Okay, so proposition. So let G be a matrix Lie group, which is closed under conjugate transpose. Transpose that. So that means that is really. That is, if A belongs to G, then A star, really A bar transpose, this belongs to G. Okay. So then this is a very simple. Then G is equal to Lie algebra of G is closed under is also closed under conjugate transpose. So that is really very easy proof. So let this thing let X belongs to G. This implies e to the power Tx belongs to G for all T belongs to R. That means e to the power Tx star belongs to G for all T belongs to R because this is closed under conjugate transpose. This is really e to the power Tx star. This will belongs to G for all T belongs to R. Since the group is closed under conjugate transpose, this implies by definition this will be X star belongs to G. So this finishes the proof. Okay. Now the thing is okay, so we want to give you some examples of RSS, RSP, and RSS. So, okay. So first example, of course we will want to do this Euclidean case. So let M is equal to really Rn. Then G is equal to this I Rn naught, and this is some semi-detached part of SON and Rn. So you know that in abstract algebra, if H is a subgroup of G, we write like this: H is a subgroup of G. If H is a normal subgroup of G, we like to write this. So what you do this Rn and this is SON. Since Rn is normal, so we will put like this. So this is a semi-direct product of Rn and SON. Now, what is the group law? You take this VA dot WB. Okay. This is B plus AW. This is AB. So this is BW belongs to Rn and AB belongs to SON. So G has an action on Rn. So what is the action? B dot B comma A dot X is equal to really AX plus B. This is the group action. This is the group action. And this X belongs to Rn. Okay. Now we know that this sigma, the corresponding involution from sigma from G to G will be this thing like sigma G is really SP GSP, where P is a fixed point. So I will fix my point 0 as the thing. So 0 is my point, P will be 0 will be my point. So B comma A dot 0 is equal to 0 if and only if this A into 0 plus B is equal to 0. This implies B is equal to 0. So hence this K is equal to really stabilizer of 0 in G is something like 0A, so that A belongs to SON, right? And this is isomorphic to SON. Now the thing is, so we have what is the geodesic inversion at the point 0? So SPX was really minus X plus 2P. Okay, if so, therefore S0X is equal to what? This is really simply minus X. And this is really S0 is an isometry. So this is really 0 dot minus I dot X. Hence S0 is equal to 0 minus I. Okay. Now I want to define sigma. Sigma of X is really what? Of sigma of G. So G is really VA. This is really S0 and VA and S0. So this 0 minus I and VA 0 minus I. So you multiply this thing. So 0 minus I VA. So first you multiply this thing B minus B and minus A to 0 minus I. And this is really minus B A. Hence the corresponding Riemannian pair corresponding Riemannian symmetric pair RSP for Rn is really is what? Rn, this thing SON, this is SON with sigma from this thing to this thing. It's given by this thing. Sigma of VA is really minus VA. So now we want to give second example. So let us use the second case. So B is really Sn minus 1. So G is equal to really ISN minus 1 naught. And this is really SON. I will fix the base point as the En plus En. So let K is equal to really stabilizer of En inside G, and this is really 0 A0 0 1. A belongs to SON minus 1, right? Good. So this is really A0 0 1. So that A belongs to SON minus 1. And this is isomorphic to SON minus 1. Now, how do I do this thing? I want to really get this SEN. So SEN, how to get this thing? You are really write this REN, RN. You write this RN is really REN plus REN for, right? And REN for is really what? TEN SN minus 1. And this is really span of this E1, E2, EN minus 1. Okay. Now on REN, this is really SEN is identity. If you have followed my past lecture, and on REN plus N power, since REN power is TEN SEN minus 1, this SEN is equal to minus identity, right? Hence, now therefore what SUN will be, what SUN will be matrix belonging to ON. So on REN this is identity, and REN perm this is minus identity. So SEN will be something like minus identity 0, 0, 1. And this minus identity is a n minus 1 cross n minus 1 matrix. Okay. And there is, this is really, we have used this notation. This is really minus of I minus 1, 1. Okay. So remember this IPQ is the notation. This is really IP plus P matrix and minus IQ plus Q matrix. This notation we has really used this thing. Now the thing is, therefore sigma from SON to SON is given by sigma of A is really SEN A SEN. Okay. Now what is SEN? This is really minus of I n minus 1 comma 1 A minus of I n minus 1 1. So minus minus you will get plus. So this is really I n minus 1 1 A I n minus 1 1. Okay. Hence for SN or SN minus 1 or SN minus 1, the corresponding RSP Riemannian symmetric pair is really what? This is SON minus 1 with input sigma from SON to SON given by sigma of A is really I n minus 1 1 A I n minus 1 1. Actually we are doing these examples because that will be really, we will get some clue from these examples to define involutions in more complicated cases. Okay. So these examples are very important in the first thing. Now C is really HN. So for HN, this I HN G is equal to IHN naught. This is really SO naught N1, right? And I will fix the base point as En plus 1. Now this thing, okay, so K is equal to really stabilizer of En plus 1. Oh, stabilizer of En plus 1 in G. This is really A0, 0, 1. This A belongs to SON, right? Okay. And this is really a isomorphic to SON. Now, similarly, I want to really determine SN plus 1. So for that reason, I have written really Rn plus 1 is really Ren plus 1 plus this Ren plus 1 perf, and this perf is perpendicular with respect to this this bilinear form which is which we have which is used to define this SO naught N plus SO naught N1, and this is really on this thing. This is really SEN plus 1 is identity, and this thing is really SEN plus 1 is really minus identity. And what is R En plus R En plus 1 for? This is a real Ten plus 1 Hn, and this is same thing as like sphere span of this thing E1, E2, En. Okay. Now for that reason, what will be this Sen plus 1? This is the same thing. This will be minus of identity because on this space span of this E1 to E1, E2, En, this Sen plus 1 is minus identity. So minus identity, and this 0, 1. So this is really n cross n matrix. Now this is really minus of In1. Hence sigma here from SO0 n comma 1 to SO0 n comma 1 is given by this thing. Sigma of A is really Sen plus 1, composition A, Sen plus 1. So this is really minus of In1 A minus of In1. And this is really In1 A In1. Now we want to really do some changes here. What you do, you multiply this A transpose inverse and A transpose, then you write whatever was there. A transpose, sorry, In1 A In1. Look at this thing very carefully. Since this belongs to SO not n comma 1 and In1 n comma 1 is the matrix which is defined, which has been used to define this group SO not n comma 1. So for that reason, this will be really A transpose inverse. This is In comma 1 into In comma 1. Okay, and therefore this A transpose inverse. This is In comma 1 square. This is really A transpose inverse, and In comma 1 square is identity. So this is A transpose. So hence, so sigma A is equal to, in this case, this is A transpose inverse. Now hence the corresponding RSP is really SO0 n comma 1 SON with sigma of A is really a transpose. Santanu, is this clear?
Yes, Manoj.
Manali.
Yes, it's clear.
Okay, so this is the thing. Now we really come back to a question which was asked by SKR in one of the previous lectures. Suppose Hn is equal to, we know that we have some geometric description of Hn are there now, but we suppose this is not our definition. This is our definition is something like suppose Hn is really something like SO0 n comma 1 mod SON, and this is my definition. Okay, this is my definition, and I describe the geodesic inversion. And here actually you can define this is my involution. Sigma A is equal to really A transpose inverse, and this is SO0 n comma 1, and this SON is a Riemannian symmetric pair. Okay, so now I want to really describe this so-called geodesic inversions. So what I will do, I will this is thing S of O means S of K. So if you look at that theorem, S naught of GK GH. Okay, so what I am saying that in that theorem, okay, if G, okay, so let us write here. in that theorem, if GH is a Riemannian symmetric pair, so S naught, okay, GH was given by this thing, sigma G of H. Okay, and what was this S of sub MH GH? This was given by this M S naught. Okay, this M inverse applied on GH. Okay, if you have you in that theorem. Okay, so this therefore this S of K is your SON. So K is really SON. So that means this is SK and some AK is given by this thing sigma of A into K, and sigma A is really A transpose inverse K. Now what is S of BK applied on AK? K should be bigger. It's B SK B inverse. This is AK, and this is really you can calculate now. B SK B inverse A. This is really B inverse A K. Okay, so it's B dot SK B inverse A. This is really you apply this thing sigma GH, and sigma is here B inverse A inverse
Mona, just a
transpose.
minute.
Yes, sir.
Just a minute. In the green, what you have written,
Yes, sir.
your M is just any element of the group or something else?
M is any element of the group.
Okay.
This is easy, sir. If you describe the sigma, then from that.
No, I got confused with M. I got
Yes,
confused
yes.
with the symbol M.
Actually, I don't want to write H because that will. So, can you suggest a good symbol?
Maybe I don't know. Any other element of the group is very difficult.
Actually, it is very in this lecture. Actually, writing
M
this
is
book.
M is little dangerous.
Yeah, little. Yeah, can I proceed now?
Yes, please carry on.
Yeah, so SK is equal to you have to just calculate that there is nothing to B, and this is really A inverse this B transpose K, and this is really B transpose A transpose inverse K. This is the thing. So there is no issue about it. Okay, so this is the thing. Now I want to give some more examples of Riemannian symmetry sphere and discussion. This is a so let G subset of GLNC be a matrix Lie group which is really closed under conjugate transpose. Now, okay, so G subset of GLNC is closed under conjugate transpose. Now I define a involution from G to G, and for matrix Lie group there is a natural involution. Define sigma from G to G by sigma of G is equal to G transpose inverse, right? Oh, sorry, G conjugate transpose, G star inverse, or and this is same thing as G inverse star. Okay, so this is an group homomorphism and group automorphism. Clearly, sigma is a group automorphism. Okay, and sigma square is identity. And group automorphism means this is actually smooth. Actually, I am assuming that this is smooth. And the group automorphism means that this is smooth actually. Now sigma G is equal to G. This implies this This is if and only if G inverse star is equal to G. So this is really will give you G star is equal to identity. That means G is really G belongs to UN. Now I want that this group automorphism should be an involution. That should not be identity. For that reason, I take a condition and G subset doesn't properly contain inside N. I will take a condition like that. So that will implies since G is not really contained inside UN, therefore this G sigma is an involution. Now from this step, what you are getting from star, actually it is you are getting that what is G sigma. Oh God, I have to add 1 or 2 pages. Okay, so let us see. Okay, so this is the thing. Now from this stage, actually, therefore sigma is in involution. From star, what we will get from star, we get that G sigma. G sigma is the set of really fixed point of G. G belongs to G, so that sigma G is equal to G. This is really G intersection UN. Okay, and we have seen that G intersection UN is compact. So it's compact. Now if H is a closed subgroup of G, so that this thing happens, so that H is contained inside G sigma, and this is G sigma naught. Clearly, this since G sigma is compact, so therefore this clearly H is compact because G sigma is compact. Okay. Now then it is also clear that the GH is a Riemannian symmetric pair. And with the involution, of course, this is the involution. Sigma is equal to G inverse star. Now let us see that what will be the Cartan involution, and so what will be the Cartan? Let theta is equal to really D sigma be the Cartan involution. So let x belongs to G. Okay, so what is theta x? Theta x is by definition. Theta x is by definition d by. Okay, so d sigma ex. And what is this? D by dt of t is equal to 0. Sigma of exponents e to the power tx. Okay, exponential of tx. And so this is d by dt of t is equal to 0. The exponential of this, we are in a matrix Lie group. This x star e to the power tx inverse star. Okay, so d by dt t is equal to 0. This is really e to the power minus t x star, and this is really minus x star. So hence theta x is equal to minus x star. Now k is equal to x belongs to G, so that theta x is equal to really x, and this is really x belongs to G, so that theta x is equal to minus x star, so x is equal to minus x star. That means this is G intersection the skew Hermitian matrices. Okay. Now P is equal to what? X belongs to G, so that theta x is equal to really minus x. And if you put that theta x is equal to minus x, this will you get really x is equal to x star. So G intersection Hermitian matrices, right? Now if x belongs to G, the Cartan decomposition is really x is equal to x plus theta x by 2 plus x minus theta x by 2. And this was really belonging to K, and this belongs to P. So if you will apply that thing, this is really x plus theta x is equal to minus x star, right? Minus x star by 2 plus x star by 2. Okay, so this is the thing, and we will apply that the theorem. But this is for GLN matrices. Okay, for this GLN R matrices, we have the same thing will work, but instead of star, you have to really take only transpose, and there will be some minor changes. So let me write that. So and that will be also a special case of this thing. So if G subset of GLNR be a matrix Lie group closed under transpose, and G is really not subset of ON, then sigma from G to G will be given by sigma A is equal to really A transpose inverse, and sigma is given by A transpose inverse, and what okay, and in G sigma will be, and G sigma is equal to G intersection ON. So if H is a closed subgroup of G with this thing, H is subset of G sigma naught, subset of G sigma, then GH is really is a RSP, and what will be K here? K will be this G intersection really anti-symmetric matrix. Okay, so anti-symmetric matrix, and P will be here G intersection symmetric matrix. Right? And this Cartan involution theta will be theta, or x belongs to G. So theta x is equal to really x transpose inverse, and Cartan decomposition x will be really x plus x minus x transpose by 2 plus x transpose by 2. And this will belong to really K. Yes, sir.
Why X transpose is inverted?
What you are saying, sir?
Theta X is X transpose inverse or minus X transpose?
Oh God. Oh, sorry, sir. Thank you, sir. Minus x transpose. Actually, I am doing this thing. This is okay. So theta x is minus x transpose. Okay, that's okay. Now the thing is, we are ready to apply this two discussions to get new example of Riemannian symmetric space. We have given enough example of group G, and we have also calculated this called G intersection of ON. And for the Riemannian symmetric pair definition of Riemannian symmetric pair, we need connectedness, right? G is a connected Lie. So I have left that somehow. Matrix Lie group, G be a connected matrix Lie group. Okay, so here you have to assume that is G be a connected. Okay, so matrix Lie group, sorry. And here also we have to assume that GBA connected. Okay, so I have given you example. So I have given you examples of this Lie groups for which I have calculated this G intersection ON. And since this G is I am taking connected GL plus 1 NR, if is that group G intersection ON is SON, and that is really connected. Everything will be here connected. So GL plus NR mod SON is a Riemannian symmetric space. SLNR mod SON is a Riemannian symmetric space. So you will get everything which I have written here. These are really symmetric spaces. Okay. So since G is connected, and I have shown that connectedness of G really boils down to connectedness of G intersection UN. Okay. So in this case, G intersection UN is connected. So you will get only one H here. And what is G intersection UN? G intersection UN is the maximal compact subgroup of G. So these are some new examples: GL plus NR mod SON, SLNR mod SON, SO not PQ mod SOP cross SOQ, SP2NR mod UN, GLNC mod UN, something like that. So you can see that list. Okay. So one thing about we will not able to discuss everything, but we will certainly discuss one or two examples in very detail. For instance, SLNR mod SON, we'll discuss it, and something hopefully I will discuss this. Okay, so these are some new example of Riemannian symmetric space, which are non-compact Riemannian symmetric space. I am not saying that these are symmetric space of non-compact. I am just saying that these are non-compact Riemannian symmetric. So I want to give some examples of compact Riemannian symmetric spaces now. Okay, compact Riemannian symmetric spaces. Okay. So first thing is really you take this example that G is equal to SON. Okay. So we want to define an interval depend sigma from SON to SON by this thing.
Muna, did you prove that any connected compact group is compact symmetric space earlier? Any connected compact group is symmetric space?
Actually, I will do. Yeah,
You
I have
proved
proved that. I have proved that.
So from there,
You need Lie group, compact connected Lie group.
Any compact connected Lie group is a symmetric space. I have proved that. Because the thing is, I have shown you that this if a Lie group has a bi-invariant Riemannian metric, then that is a Riemannian symmetric space. And I have proved that if RG is compact, then there will be some bi-invariant Riemannian metric. Therefore, that will be a Riemannian symmetric space. Since if G is compact, then RG is compact. Therefore, that is a Riemannian symmetric space.
okay, but here you are defined something different.
For a G is equal to SON, actually this is not a symmetric space. I will, of course, this will be symmetric space, but I am defining differently.
Okay.
So sigma.
Question here to Sanjay.
Yeah.
Sanjay, are you asking that if G is a compact connected Lie group, it's of course a symmetric space, but what is the corresponding symmetric pair? Are you asking that question?
No, not. I am not asking that. Just I was just saying that. I
Okay.
thought that you proved that these.
Okay, that is an interesting question. We will do that in next lecture. That if G is a compact Lie group, what is the Riemannian corresponding Riemannian symmetric pair. And but you have proved this thing. If G is a compactly group, that is a Riemannian symmetric space. Okay, so let's define sigma from SON to SON by. Okay, if you define like this, sigma A is equal to A transpose inverse, then that will not work because SON this will be precisely A. So we have to define in a different way. For that reason, that example of sphere is necessary. So in the case of sphere, what was the thing? The group was compact SON, but it was really conjugation by something in minus 1, 1, right? And we will use that idea to prove that. So this is really 1 less than k less than 1. This is really I k n minus k a I k n minus k. So since this I k n minus k, this belongs to ON, and this is really its own inverse. I k n minus k square is equal to identity. So this implies sigma is a proof automorphism. This is smooth group automorphism actually. Group automorphism means that is smooth, and sigma square is identity because this is just a conjugation by I k n minus k, and I k n minus k is a product. Now let sigma A is equal to A. That means this is if and only if I k n minus k A I k n minus k is equal to really A. This is really I k comma n minus k A is equal to A into I k into n minus k. Now let this thing A is equal to really x, y, z, w, and you partition x, y, z, w appropriately. For instance, x is a k cross k matrix, y will be some k cross n minus k or something like that. You just partition accordingly. But what so I k n minus k A is equal to I k n minus A into I k n minus k. What does that mean? That means this is k cross k. Okay, 0 minus I. This is n minus k cross n minus k. This is really x, y, z, w. This is really x, y, z, w. This is really I 0, 0 minus. Okay. Now this is behaves like elementary matrix multiplication. You are multiplying row. By left you are multiplying in the row. By right you are multiplying. If you multiply elementary matrix in the right, you are multiplying the columns actually. So this will be give you what? This is really x, y minus z minus w is equal to really x, z minus y minus w. And from there you will get what? Now y is equal to 0 because y is equal to minus y and z equal to 0. Now, so this is thing. So that means okay. Now what is this x? This implies a is of the form. Okay. A is of the form x 0 0 w, right? And this will belongs to really SON if and only if this S belongs to actually x is a k cross k matrix. This is a k cross k matrix. X belongs to SOK and W belongs to SO. No, sorry. This X belongs to OK. W belongs to ON minus K. And determinant of X and determinant of W is really 1. So I call this thing that, let us say this star. Okay, and okay. So from these things actually, so hence what we will get? Hence we get this G sigma is equal to really, this is SOK cross ON minus K. So now we have this condition actually means that G sigma is equal to really S of OK and this O minus K. So we have shown that we have seen that this G sigma has two connected components. And this G sigma naught is really SOK plus SON minus K. Now the thing is, so if H subset of G is closed and this H is really contained inside G sigma naught contained inside H subset of G sigma, then this either this H is equal to either G sigma or H is equal to G sigma naught. So in this case we get two Riemannian symmetry here. So in this case we get two Riemannian symmetric pair. So first is something like first is your what? First is really SON. This is SO S of OK plus ON minus K. I am taking this first H is equal to G sigma. So and the corresponding Riemannian symmetric space is what? Riemannian symmetric space is really SON mod S of OK O cross ON minus K. And if you look, I have actually what is this? This is actually GKRN. We have discussed this in some classes. This is really Grassmannian of K-planes. K-plane in Rn. So we have discussed this thing. Now the second example is something like this. I have to take this thing SON. This is really SOK cross SON minus K. Okay. And what is the corresponding Riemannian symmetric space? Corresponding Riemannian symmetric space is really SON mod S of SOK cross SON minus K. And what is that? This is actually people write as a GRK not Rn. This is actually, this is the definition. You can take this thing. This you can really identify with oriented Grassmannians of K-planes in the Rn. So I will tell something about in the next lecture probably. Better K-planes in Rn. So in case of if you look at this thing, if you look at this SON and you define this in the involution sigma A by like this, then in this case we are really get two Riemannian symmetric pair. One is Grassmannian of K-planes in Rn. This is another thing oriented Grassmannian. Now second example, I can really second example, let G belongs to UN. I can play the same game. So let sigma from UN to UN be given by this thing. Sigma of A is really IK composition N minus K, A IK composition N minus K. Okay, so this in this case, what will be G sigma? G sigma is really UK cross UK cross UN minus K, and this is really compact and connected. So, since this G sigma is equal to G sigma naught, these two things are same. Therefore, H will has to be G sigma or G sigma naught in this case because this is connected. So hence the corresponding Riemannian symmetric space is really what? Or Riemannian symmetric pair is really what, UN, and this is UK into UN minus K. Actually, in books you will not write, you will not see this cross. Actually, they will simply write UK into UN minus K. That by that you mean just this is cross, and with corresponding RSS, with RSS is equal to really UN mod UK cross UN minus K. And what is this? This is the GKCL. This is really Grassmannian of K planes in CN. K planes in CN. So now let us prove another example. C is really, let G is equal to SUN. Then this sigma, I will define the same thing. Given by this thing, sigma of A is equal to sigma is IK n minus K, A, IK n minus K. And what is G sigma here? G sigma is really S of UK plus UN minus K. And this is what? Okay, this is really compact and connected. Hence, we will get one Riemannian symmetric pair. Hence, this thing SUN SUK plus UN minus K. Okay, so is a RST, and corresponding RSS is what? Is really SUN. This is really SUN mod S of UK plus UN minus K. And this same thing as GKCL. So in this case also you get this GKCL. So you see that these are two different Riemannian symmetric pairs, but this give rise to same Riemannian symmetric space. So remark. So the okay, the Riemannian symmetric pair UN UK cross UN minus K, and this SUN S of UK cross UN minus K give rise to the same Riemannian symmetric space GKCL. Okay. Okay. Now I just D. Okay, so D is really what? G is equal to SPN. This sigma. Okay. To SPN be given by this thing, sigma of A is really IK n minus K, A IK n minus K. This is 1 less than equal to K, and then G sigma is really what? SPN. Oh, this thing is SPK plus SPN minus K, and hence and this is connected and compact also. Compact. Hence this SPN SPK plus SPN minus K is a Riemannian symmetric pair with the corresponding RSS is really thing. Okay, SPN mod SPK cross SPN minus K, and his with is GKHN. This is really Grassmannian of K planes in CN. HN Grass of K planes in HN. So this is the thing. Now actually I wanted to give 2-3 more examples, but I don't have much time with me. So with this I would like to stop. If you really want to ask me any questions, you can ask from today's lecture, or any exercise or any doubt from the previous lectures also you can ask. And in the next lecture we will give some more examples of compact Riemannian symmetric spaces. And you also okay, and also I have told you that I want to take this Friday's lecture on Thursday. So if you have any problem with that, you can also tell me. So is there any questions, Anway or Tapendu, Riju? Mithunda? You are there now. No question? Rajesh, will I stop?
Yeah, should I start?
Yeah, start. Then nobody's asking, then you should stop.